Welcome to my workshop. I'm Jim. Today I want to share with you what I've learned about using light-emitting diodes. If you're only interested in the rule of thumb to be used during design, then just skip ahead to the point 14 minutes and 15 seconds into the video. Otherwise, let's get started. I've already wired up a small breadboard. I've plugged in 17 resistors whose values decrease from left to right. The resistor on the left is 33,000 ohms or 33K. The label here above shows the value of every second resistance. The resistance down at this end is 10 ohms. The resistance in the middle here is 1K. I've plugged in 15 LEDs in series with the resistors. I haven't yet plugged in these two LEDs over here. All of these branches are in parallel with each other, so they're all powered by this battery, which is a nominal 7.4 volts. I'm now going to plug in the LED, which is in series with the 22 ohm resistor, and the last one in parallel with the 10 ohm. Oh, I can see that this one on the end is already starting to get a little bit dim. All of these LEDs in this range here are really too dim to be of much use. All of these LEDs out to here have the same brightness. They would all be satisfactory. This LED at the end is starting to grow dim, and I think this one next to it seems to be growing dim as well. Just in case the intensity is overwhelming the camera, I've tilted it up to show what the LEDs look like from the side. What's happening is that the high resistors down here don't let enough current through. And without enough current, the LEDs are too dim. Over here, the resistors are so small that they allow a lot of current to go through. So much current that they actually seem to be burning out the LEDs. That last one is actually pretty hot. It's not sizzling hot, but it's really too hot to touch. I'm going to put the board to one side for now. I'll come back and have a look at it in about 10 minutes. This is a schematic diagram of the components which are mounted on the breadboard. There are 17 branches, each branch consisting of a resistor in series with an LED. All 17 branches are wired in parallel and driven by that battery on the left-hand side. Although the nominal voltage of the LiPo battery is 7.4 volts, I measured it with a voltmeter and found it to be 7.51 volts. The battery's a little bit overcharged. I've put a row in below the schematic which sets out the resistor values in each branch. As I said before, the resistors range from 33K on the left all the way down to 10 ohms on the right. We've already seen that on the left-hand side where the resistor values are high, the LEDs are too dim. Over on the right-hand side, where the resistor values are low, the LEDs are burning too hot. There's a region here in the middle, say with resistances between 1K and 220 ohms, that seems to be a good balance between brightness and heat. What I want to do is figure out what the relationships are so that I can calculate the most suitable resistance to use when the voltage is something other than 7.4 volts. The way to start is to measure the voltage drops over the individual LEDs using a voltmeter. The red arrow shows the voltage drop from the positive side to the minus side of each LED. For the LED in series with the 1K ohm resistor, I measured the voltage drop as 1.85 volts. Moving the voltmeter over to the right, to the branch with the 33 ohm resistance, I measured a 3.93 volt drop. The bottom row in the table now shows the voltage drops for all of the branches. Observe that the voltage drop is about 2 volts all across the range, except at the very right side where the resistor values are low. Over on the right-hand side, the voltages seem to climb pretty quickly, all the way through 3 volts, 4 volts, up to almost 6 volts. What I'm going to do next is calculate the voltage drop over the resistors. The red arrow now shows the direction of the voltage drop from the positive end, the top end of each resistor, to the negative bottom end. After I've calculated the voltage drops over the resistors, I'll then move on and calculate the current flowing down through each branch. In order to calculate the voltage drops over the resistors and the currents flowing down through the branches, I'm going to look at the individual loops in the circuit one at a time. I've shown, highlighted in gray here, a single branch. That's the one that contains the battery, the 1K resistor, and the LED in series with the 1K. The battery voltage is 7.51 volts. I measured 1.85 volts absorbed by the LED, so the rest of the applied voltage, being 5.66 volts, has to be the voltage drop over the resistor. You've probably done this kind of subtraction lots of times before without knowing that you're actually using Kirchhoff's law. It was a guy named Mr. Kirchhoff who figured this law out. The way he explained it, the sum of the voltage drops around any closed loop has to add up to 0. I've shown with a green arrow here a closed loop, and we're going to traverse this closed loop in a clockwise direction. The voltage drop over the resistor, which is the arc in the upper right quadrant, is 5.66 volts. The voltage drop over the LED, which is the arc in the lower right quadrant, is 1.85 volts. The voltage drop over the left-hand arc is minus 7.51 volts. It's minus because the voltage does not drop as we go clockwise. Instead, it goes up. An increase is the reverse of a drop. And when we're adding numbers, we'll put that in as a negative number. Adding up these three voltage drops around the green loop gives 0. That's Kirchhoff's law. Now, just to finish things up, I've taken the 5.66 voltage drop over the 1K resistor and entered it down in the table. In the next step, I'm going to apply Ohm's law to the 1K resistor. We've calculated that the voltage drop over the resistor is 5.66 volts, and we know that the resistance itself is 1K, or 1,000 ohms. Actually, to be a little more precise, it's not 1K. It turns out to be 1,010 ohms. I measured it with an ohmmeter. Recall that Ohm's law is that voltage V equals current I multiplied by resistance R. Voltage equals current times resistance. That's an equality. Both sides of the equality have the same value. When you have an equality, we can divide both sides by any number, like 13, and both sides will still be equal. But dividing by 13 doesn't serve any useful purpose. On the other hand, we get a big advantage if we divide both sides by the resistance R. Resistance R is now on the top and the bottom of the term on the right-hand side. We can cancel out those two R's, and what's left is simply the current I. This equation, voltage divided by resistance gives the current, is one of the three variants of Ohm's law. In the present case, 5.66 volts divided by 1,010 ohms gives a current of 0.0056 amperes. 1 ampere is a huge current. It represents a really big number of electrons whizzing by in a wire every second. Most low-power circuits, which we would play with on a desktop, have currents that are only a fraction of an ampere. Therefore, it's often more convenient to measure currents in milliamps. A milliamp is 1,000th of an amp. You can remember that by remembering that a millipede has 1,000 legs. So a current of 5.6 milliamps is flowing through the 1K resistor and through the LED that's in series with it. I'll now enter that current, 5.60 milliamps, into the table. I completed the second to last row in the table. I used Kirchhoff's law for each of the 17 branches and filled in all the voltage drops over the resistors. Finally, I applied Ohm's law to the resistor in each branch and calculated the currents in milliamps, which I filled in the last row of the table. Now here's the completed table. The bottom row is the one that I'm interested in. The currents through the 17 branches range from a low of 0.18 milliamps on the left-hand side, all the way up to 191 milliamps on the right-hand side. I have to say that I was very surprised when I did these measurements and filled out the table. I've used LEDs for many years, but I've never used one with a current of more than about 20 milliamps. I didn't realize that an LED could survive using a current more than 20 milliamps. I'd always assumed that driving a current of 100 or 200 milliamps through an LED would cause it to pop like an old incandescent light bulb. And after it popped, I thought that the burnt out shell would be an open circuit. But that doesn't seem to be the case. Instead, it looks like the LED grows dark, but allows current to continue to flow through. I've drawn a black rectangle around the range of currents that seems to be best between 5 milliamps and 20 milliamps. In a sense, this is a sort of Goldilocks region that represents a good balance between being too dim and being too hot. Now, numbers in a table like this are difficult to comprehend, so I've graphed them. I've plotted the voltage drop over each LED versus the current flowing through it. For example, the leftmost branch, which has a 33k ohm resistor, had a voltage drop over the LED of 1.6 volts. I've plotted that here, and it's about a third of the way up the vertical axis, which stretches from 0 volts to 6 volts. The current through that LED is 0.18 mA, which is very small. It's almost at the 0 point on the horizontal axis, which runs from 0 to 200 mA. The other extreme is represented by the branch with the 10 ohm resistor, and its operating point is way up in the right-hand corner of the graph with a voltage drop over the LED of about 6 volts and a current of about 200 milliamps. I then filled in the plot with the points for the other 15 branches, but I noticed that there's actually one more data point. When the voltage drop over the LED is 0, obviously no current's going to flow through it. That's the 0, 0 point on the graph. I connected the data points with a continuous line to complete the curve. The Goldilocks region that I talked about before is only a very small part of this graph. It's the range from, say, 5 to 20 milliamps. I've highlighted that little area with a green rectangle. When you buy an LED, the label on the package is going to include a current. Very often, it will be 20 milliamps, but it sometimes could be as low as 10 milliamps or even as high as 25 milliamps. This current is the manufacturer's recommendation about the maximum current to which the LED should be subjected. The arrow that I've shown here at the bottom of the graph shows the typical maximum current recommended by the manufacturer. When you use a manufacturer's LED properly, the LED will have a very, very long life, maybe 50,000 hours. That's 7 years of continuous use. But we've already seen that if you use a current that's greater than the manufacturer's recommended level, you'll greatly shorten the life of the LED. The next slide I'm going to show is a blow-up of part of this graph. It's the part that's inside the black rectangle. Here we are. This kind of graph, which is a plot of the voltage drop over a component versus the current through a component, is called the VI characteristic, the voltage current characteristic. And one can produce a VI characteristic of any component, not just an LED. And the range of interest is the range that I've highlighted with another black rectangle. What's really interesting about that is that the voltage for all the currents in that range is very close to 2 volts. In other words, the voltage drop over any LED which is properly biased is going to be close to 2 volts. That leads us to the design rule of thumb that I'm going to explain next. That's the rule of thumb you're going to use when you want to put an LED in one of your circuits. Suppose you have a circuit, any circuit, and that there are 2 points, A and B, in the circuit, between which you want to have a visual indicator of voltage. Your goal is to add a visual indicator to show whether the voltage drop from A to B is 0 or some other voltage. I'm going to assume that that other voltage is V test. In your circuit, V test might be 3 volts. In the breadboarded circuit we looked at above, it was 7.4 volts. There's really no limitation on what V test should be. To achieve the goal, you insert a branch between A and B, which has an LED in series with a resistor. A resistor, when it's used in series with a component like this, is a current limiting resistor. The resistor controls how much current flows through the branch. Step 1 is to set the voltage drop over the LED to 2 volts. Step 2 is to observe that the voltage drop over the resistor will therefore be V test minus 2 volts. Step 3 is to choose the desired amount of current. I always set it to 5 milliamps. I've never had any problem using LEDs with 5 milliamps, even when using them in bright sunlight. Step 4 is to use Ohm's law once again, but this time using Ohm's law to calculate the appropriate value of the resistance. As always, Ohm's law is that the voltage equals the current times the resistance. V equals IR. Once again, that's an equality, and we can divide both sides of an equality by any number we like 3. But a better choice is to divide both sides of the equality by the current I. You'll note that the current I then can be crossed off from the top and the bottom of the term on the right-hand side, which reduces to just the resistance. This is the third variant of Ohm's law, where the voltage divided by the current is the resistance. In our case, the voltage drop over the resistor is V test minus 2 volts, and the current we want to flow is 5 milliamps or 0.005 amps. When we do the division, the result is going to be the resistance in ohms. Let's look at an example. If your circuit's going to be running at 24 volts, then the voltage drop that you want over the resistor is going to be 24 minus 2 or 22 volts. Dividing 22 volts by 5 milliamps gives a resistance of 4,400 ohms. The standard value resistance that's closest to that is 4.7K. A 4.7K resistor would work perfectly in this situation. Polarity matters for an LED. For a resistor, current can flow either way. You can take a resistor out of a circuit, switch it around end for end, and put it back in, and you won't observe any change. Not so for an LED. LEDs have to be wired into a circuit in the right orientation. If the LED is put in backwards, it just won't work. Like any diode, and an LED is just one kind of diode, current flows from the positive end to the negative end. When you see the symbol for an LED in a schematic, how can you tell which is the right direction? The trick is this. Treat the little triangle in the symbol for the LED like an arrowhead. And like an arrowhead, it points in the same direction as the current has to flow. When you're looking at a real-life LED, how do you tell which end is which? I've shown here a picture of an LED seen from the side. The LED part of things is the small cylinder at the top. The one shown here has a domed top. There's a small lip around the bottom of the casing, and 2 wire leads extend out axially below the bottom of the casing. One of those leads is always longer than the other, and the longer lead is the plus side. The shorter lead is the minus side. How do you remember this? Well, you note that a plus sign has height. A minus sign doesn't have that height, and that extra height corresponds to the extra length of the longer lead. There's another way, a second way to tell the polarity on physical LEDs if they're round. When you look down from the top on a round LED, you'll see that the lip at the bottom of the casing is not uniform all the way around. The lip has a flat side, and the flat side corresponds to the minus sign. You can remember this by noting that the minus sign is able to snuggle up right alongside the flat, and the plus sign can't do that. I want to take a minute just to explain why the design rule of thumb actually works. Why is it that the voltage drop over an LED is always really close to 2 volts? The answer lies inside an LED. Inside an LED, there's 2 small blocks of material. You can think of them as 2 little cubes which are pressed up against each other. And the face where they're in contact is called the junction. One of the exterior leads is connected to one of the two blocks, and the other exterior lead is connected to the other little block. Both blocks are made from the same basic material. This material is called a semiconductor because it's chosen to have some of the characteristics of a conductor, like a metal, and some of the characteristics of an insulator, like glass. This material is a solid, and all that means is that the individual atoms are fixed in position in a three-dimensional matrix. They don't wander around like atoms in a liquid or atoms in a gas. Consider first the little block that's on the right. To make an LED, the manufacturer removes some of the atoms out of the three-dimensional matrix and replaces them with atoms which have the next higher atomic number. That means that the replacement atoms have one more electron in their outer shells than the atoms of the semiconductor. These new electrons are held only loosely by their parent atoms. It doesn't take much energy to coax them to move from one atom to a neighboring atom. But note this, these electrons are not extra electrons like those which float around on the plates of a charged capacitor. Nope. This entire block of material is still electrically neutral. You wouldn't get a spark if you touched it. The only thing that's different is that these electrons are easier to move from one atom to the next. The block on the left is also treated. In this case, the manufacturer removes some of the atoms from the matrix and replaces them with atoms which have the next lower atomic number. That means that those atoms that are put in place have one fewer electrons in their outer shell. These atoms, therefore, have a tendency to want to accept an electron from their neighboring atoms. In essence, these atoms which are put in have an extra spot on the outside of their electron shell which they want to have filled. These extra spots are referred to as holes. And when a hole jumps from one atom to a neighbor, it leaves behind another hole. In fact, these holes move around almost as if they were positively charged electrons. Now, once the two little blocks of material have been treated, they're called p-doped and n-doped material. The p stands for positive and the n stands for negative. When a voltage is applied over the LED with the holes to the n side with the electrons, then the electrons will tend to move towards the left, and the holes will tend to move towards the right. And the sum of these two movements is the current I, which we would measure flowing through if we have used an ammeter. The interesting thing happens when an electron comes up to the junction and tumbles over from the n side to the p side. When it tumbles over, the electron loses some of its kinetic energy, some of its energy of motion. And a part of that energy is converted into heat, but the rest is converted into a photon. And that photon comes zipping out of the junction at the speed of light. And depending on the energy of that photon, our eye would see it as being red or green or blue. Now, the energy that's in the photon is related to the energy which an electron loses when it crosses the junction. And that amount of energy doesn't depend on how big the LED is or the shape of the case or the length of the leads. The energy transferred to each photon is a fundamental property of the junction itself. And that's why we can say that for proper use of an LED, there has to be a 2-volt drop across the junction. Before concluding, I want to just mention a special kind of LED, a 7-segment LED. Just like the discrete LEDs I've talked about so far, 7-segment LEDs are used as indicators. They tell us something about what's going on inside a circuit. 7-segment LEDs are geared to display individual numbers from 0 to 9. A 7-segment LED, it's a little chip, a ½ inch high or so. It usually has a row of pins along the bottom and another row of pins along the top, although the two pins might be up and down the two sides. The numbers are produced by illuminating 7 individual LEDs. Each of these individual LEDs is a short bar, and they're oriented in a way to make them resemble the number 8. In fact, when all 7 of these LEDs are illuminated at once, what you see is an 8. The individual segments are always referred to by letter, from the letter A to the letter G. If the device also happens to have a decimal point, which many do, it will be an 8th LED, and it will be referred to as DP. If you look at a schematic diagram of what's inside a 7-segment LED, you're going to see 8 individual LEDs, all of them with their negative ends connected together. There's a separate pin on the outside of the device for the high side of each of the individual LEDs. Normally, a 7-segment LED chip will have 10 pins, 1 for each of the 8 segments, and 2 pins for the low side. The low side is called the common and is described with the acronym COM, and there's 2 pins for that side so that 1 pin can be put in one row and another pin can be put in the other row. That makes it a lot easier to physically wire up a 7-segment LED when it's put into a circuit. Note this. Each individual LED inside a 7-segment LED has to have its own resistor. I'm now going to return the focus to the breadboard. I'm bringing it down. It's been running for about 20 minutes, and during that 20 minutes, 2 more of the LEDs here on the right-hand side have burnt out. Their resistors are too low. There's too much current flowing through. Yes, I can still feel a bit of heat from these 2 here. All of these in this range look acceptable. What I'm going to do now is wire up a 7-segment LED. I'm plugging it in. I've connected the segments so that only 6 of them are lit, 3 along the bottom and 3 along the top. Each of the segments on the bottom has its own resistor. This little 7-segment LED is convenient because the common pin on the bottom row is right in the middle, and the common pin on the top row is also right in the middle. Since each of the 3 segments on the bottom has their own resistor, which happens to be a 510 ohm resistor in each case, all of them burn at the same brightness. The 3 along the top, I've actually connected them together and powered them through a single resistor. What you see is a noticeable difference between the brightness on the top and the brightness on the bottom. You need a separate resistor for each segment if you want them all to burn with equal brightness. When you change from a number to another number, and the 2 different numbers have different numbers of segments illuminated. LEDs with axial leads are great for use on breadboards. You just push them in. They're also equally convenient on printed circuit boards. You can just push them through the 2 holes you drill in the board. But what if you want to use them on a finished product? The secret is to use little plastic mounts like these. They are hollow cylindrical shells which you can press through a hole that you drill in the panel. The plastic will deform, and it's the deformation that will hold it in place. Once it's in place, you can take a standard size LED. This is a T1 3/4, and it slides into the back of the mount like that. I normally use a drop of epoxy glue to hold it in place. The advantage of mounting this way is that you can mount the LED from the back of the panel even if you have already wired it to your printed circuit board. If worst comes to worst and your circuit board doesn't work, you can always punch out the LED and then, using a knife, cut the plastic shell out of the hole. That will leave your panel with no damage, and once your circuit board has been repaired, you can put in a new shell and insert a new LED from the back. They're perfect. This is a project box where I've mounted LEDs using these mounts. On the inside, you can see that there's 4 little LEDs. And on the outside of the box, you can see how the LEDs poking through their black mounts make a reasonably tidy outside for your project. I'm going to conclude with a philosophical question. How do the resistor and the LED talk to each other? How do they work together to figure out what they should do? Thanks for watching. See you next time.